Consider omega is cosine of 2 pi over 3 plus I. Sine of 2 pi over 3 shows that omega cubed is 1. To find omega cubed, we just can apply the de Mor's theorem, and it says that omega cubed is, formula is given in the data booklet, it's cosine 2 pi over 3 multiplied by 3, it's because cubed, plus I sine over 2 pi over 3 and also multiplied by 3, and it is equal to cosine over 2 pi plus I sine of 2 pi, and cosine of 2 pi it's 1 plus I 0, so it's just 1 as required. The next shows that 1 plus omega squared is 0. And the first way is we can just calculate it. So we consider 1 plus omega squared, and it is equal to 1 plus cosine of 2 pi over 3 plus I sine of 2 pi over 3 plus omega squared. And again, applying the de Mor's theorem, it becomes cosine of 4 pi over 3 plus I sine of 4 pi over 3, and we need just calculate it. We can calculate directly using these arguments, or we can see that period is, we know that period is 2 pi and it's 6 pi over 3, and we can subtract 6 pi over 3 here and here to get in terms of 2 pi over 3 to simplify it. It's not necessary, but it's possible. We know that for any sine, cosine, we can add or subtract any number of 2 pi and we get the same value. Or we can just calculate these arguments. So it becomes 1 plus cosine of 2 pi over 3. 2 pi over 3 it's 120 degrees, and we know that 120 is the same as negative cosine of 60. So it's negative a half, plus I sine of 120, and for sine it's the same as sine of 60, it's root 3 over 2, and plus because it's the second quadrant, plus cosine of 4 pi over 3, 60 times 4, 240, it's 180 plus 60, so it's a negative, the same as negative sine, negative cosine 60, so it's also negative a half, plus I sine of 4 pi over 3, it's sine of 240, and it's the same as negative sine of 60, because it's the third quadrant, y coordinate, its sign is negative, so it's negative root 3 over 2, and we can see that we get 1 minus 1 is 0. If to subtract period, we get the next 1 plus cosine of 2 pi over 3 plus I sine of 2 pi over 3 plus cosine of 4 pi minus 6 pi. So we just subtract one period and it's the same. So we get cosine of negative 2 pi over 3. Negative 2 pi over 3 plus I sine of negative 2 pi over 3. Sine is odd function, so sine of negative is minus sine of 2 pi over 3, so it cancels, and cosine is even function, so it becomes 1 plus 2 cosine 2 pi over 3, and cosine 2 pi over 3, it's a negative a half, so it becomes 1 minus 1 is 0. And another way is to consider omega cubed minus 1. And applying the remainder theorem, we can see clearly that 1 is the root, and we know that if we know one root, we can rewrite this as, or represent it as, omega minus 1 multiplied by another polynomial, plus, in general, plus remainder, but since 1 is the root, remainder is 0. And this polynomial is 1 plus omega squared. I know it from experience because there are many similar problems, but you may divide omega cubed minus 1 over omega minus 1 and divide polynomial polynomials, or just open parentheses and see that it's the right hand side is omega cubed minus 1, so it's true. And since omega is not 1, omega is this one, omega is not 1, but we know that since omega cubed is 1, so omega cubed minus 1 is 0, so it's 0, hence 1 plus omega squared is 0. And the next, deduce that e to the power of I theta plus e to the power of I theta plus 2 pi over 3 plus e to the power of I theta plus 4 pi over 3 is 0. Definitely we should use this, and we can see that we can factor out e to the power of I theta, and it becomes 1 plus it's the same as 2 to the power of 3 plus 5, so it's 2 to the power of 3 times 2 to the power of 5, it's the same. So we just factor out e to the power I theta, and the remainder here is e to the power of I 2 pi over 3 plus e to the power of I 4 pi over 3, and it becomes e to the power of I theta multiplied by 1 plus, but e to the power of I 2 pi over 3, it's omega, but in the Euler's form, and it's omega squared. So, and we know that it's 0, so it's 0. Expand and simplify, where z is a complex number. It's quite easy, just open parentheses. So f of z is, let's open these two, so it becomes z squared minus z omega plus omega z squared minus z plus omega and minus z omega, and multiplied by z minus omega squared, and it is equal to z cubed minus z squared omega plus z omega minus z squared omega squared plus z omega squared plus z omega cubed minus omega cubed, and is equal to, and we can see here like terms. Not actually like terms, but there are terms with z squared and with just z. and it becomes z cubed minus, or let it be minus z squared, and it becomes 1 plus omega plus omega squared plus z 1 plus omega. No, we can also factor out omega, so we can factor out z omega, so it becomes 1 plus omega squared and minus omega cubed, and it's 0, so it's equal to z cubed minus omega cubed. And omega cubed is 1, so it becomes z cubed minus 1. And the next, solve f of z is 7, so it becomes z cubed minus 1 is 7, giving the answers in terms of omega, so we need just solve it. Hence it becomes z cubed is 8, and we need to find the cubed root, and we do as usual. Roots are zk is cubed root of 8, it's 2 e to the power of I theta k, where theta k is our angle, and we need to represent our complex number in the Euler's form. It's just 8, so it's 8 times 1, and 1 is e to the power of I 0. And hence it becomes our angle is 0 over 3 because cubed, or we find the cubed root, plus 2 pi k over 3. And hence the first root z0 is, we substitute 0 for k, so it becomes just 2. z1 is 2 e to the power of 0 plus I 2 pi over 3, and z2 is 2 e to the power of I 4 pi over 3, and we can see that e to the power of 2 pi over 3 is just omega, so it's 2 omega, and it's 2 omega squared. Oh, I forgot one question. Illustrate the result for theta is pi over 2 on an organ diagram. So it looks like this. When theta is pi over 2, it becomes e to the power of I pi over 2, and it's pi over 2 plus 2 pi over 3. 2 pi over 3 is it's what 60 times 2 120 plus 90, it's 210 degrees, and it's 330 degrees, so it becomes like this: imaginary part, real part. So we can just represent these three complex numbers on an organ diagram, and let's do it. E to the power of I theta, it's e to the power of I pi over 2, modulus is 1, its distance from the origin, so this number is here. Or it's just 1 cosine pi over 2 plus I sine pi over 2, x is 0 plus I1, so this distance is 1, and e to the power of I pi over 2 is represented here. And the second complex number, it's e to the power of I, and it's more useful in degrees, I, and multiplied by 210 in degrees. So again, modulus is 1, so distance from origin is 1, and 210, its argument is somewhere in the third quadrant, so it looks like this. And this is equal to this, and it's 1, and it's also 1. It's modulus distance from origin. And the third complex number, it's again modulus is 1, but argument 330, and it's here. And you can see that 30 degrees is here, and 30 degrees is here, and it looks like this. And we get the next, that sum must be 0, and we can see that if we consider the sum of real parts, it's 0 because it's symmetrical, so it's minus, it's plus, it's 0, and the sum of imaginary parts is also 0. It can be clearly shown, but it's not required here, since we know that it's 30, it's 90, so this angle is 120, this angle is also 120, and this is also 120, and using these components, so we can see that it's 30, it's 60, 1 cosine 60 plus 1 cosine 60, it's 1, so the sum of these two components is 1, but it's negative, plus 1, it's 0 as required. But finally we can see that these three complex numbers form an equilateral triangle. It's because this angle is 120, this is 120, this is 120, and this is 1, this is 1, and this is 1. So it's equilateral triangle. And that's all for this question.